All right, so now that we have introduced what Gauss's law is, let's briefly talk about how we can get from the integral form to the differential form, and then talk about analytically how you might solve it. All right, so just as a reminder, the integral form of Gauss's law we covered before is I've got some amorphous blob. Oh, it doesn't cross over. I got some little shape, and inside of that shape is a volume. And around the outside of that shape, I've got very small vectors that point outwards from the shape that we're going to call ds. ds points out from the shape, and it's got a small differential area as its intensity. So, and if we write it down in that form, then the integral around the entire surface of the electric flux density dotted with ds equals the total charge that's within that volume, right? Integral of rho v over the entire volume, all right? And then the differential form of Gauss's law that we got to get to is del dot d equals rho v, all right? So I'm going to briefly show you how you can prove that these are essentially the same thing. I'm going to set it up. I'm not going to go through the whole thing. The details will be in the notes, so you're welcome to take a look at it there. But the setup of the problem basically goes like this. I'm going to define a coordinate system in the following way. This will be the y-axis, this will be the z-axis, and this will be the x-axis. Notice this is a right-hand coordinate system, x cross y equals z. Otherwise, this would not be correct. And we're going to take a very small cube. I'm going to try my best to draw it nicely. And see how that goes. All right. Not bad. All right, and this cube is basically going to have 3 dimensions to it. There is the, stick with black, there is the delta y dimension, this over here. There is the delta z dimension, which is up and down. And there is the delta x dimension, which is delta x. All right, now this cube has 6 faces to it. All right, 2 of them are basically oriented in this plane right here. One in the front that I just shaded, and there's another one in the back. You can't see it in the drawing, but there is one back there. And so this red shaded face right here is in the YZ plane. All right. The other 2 faces are basically the top and the bottom. I'm going to draw that in blue. And the blue is in the XY plane. And again, there's 2 of those, one on the top and one on the bottom that I can't shade in this drawing. And the third one is on the side, the left side and the right side. And that is in the XZ plane. All right. So the setup to the problem is basically to sum up the contributions of each of these 6 faces. And that is relatively easy to do because the faces are considered to be flat and they're considered very small. And I'll just give you one example. For the front face, we can define the vector ds in the following way. First, the vector ds is going to point outwards from this face, right, out of the box, which means it's going to be pointed in the positive x direction. And the area is going to be basically delta y, delta z, right? So here we're going to have a delta y, delta z. What we're going to do is we are going to take the center of the box, this is black. We're going to take the center of the box, and we're going to say that that has value of d at x0, y0, and z0. If the center of the box has this value, then at the edge of the box where this ds emerges, the D field is going to be evaluated at x0 plus delta x divided by 2, and then y0 and z0, right? Since the center of this box right here is basically translated by half of delta x away from the center of the box. So taking the dot product of this is very easy. D dot ds, basically this ds vector is going to pick out only the x component of D. So this is going to be dx evaluated at x0 plus delta x divided by 2, y0 and z0. All right, the back face is going to be the same, except the ds has a negative x hat delta y delta z, right? Because that vector is over here pointed in the other direction out of the box, so it's pointed in the negative x direction. And the D field is going to be evaluated at x0 minus delta x over 2. Right? And so you can take that dot product as well. And so if you sum up the contributions of all 6 of these and sum them up, that's basically going to give you what is in this vector integral of d dot ds. Now, if you take that total integral and sum up all those contributions, and you then divide it by the volume of the box, right? So I'll just write down these steps. Sum up the 6 contributions. And then you divide both sides of the equation by the volume of the cube, which is delta x, delta y, delta z. And finally, you shrink the cube to nothing. Then you'll be left with that the divergence of the D field equals the charge density, right? Remember, the right side of this integral form is the total charge enclosed, right? This is total charge enclosed. So when you divide that by the volume, you get total charge enclosed divided by the volume, and that equals to the charge density. And then when the cube gets really small, you can basically treat that as constant within the cube. And so that's how you basically can land with the right side of this equation. All right. So in that sense, we've got Gauss's law, and we understand that it's essentially the same thing, as we had before. But how might you solve this? Well, if you happen to have a perfect analytical understanding of what the flux lines are, then you could just solve this directly. And here's the example: if D equals E to the 5x in the x direction plus 6x in the y direction plus 0 in the z direction. All right, so let's say you take an instrument and you measure the electric field everywhere throughout some space, and you fit a line to it, and you say, well, it kind of fits this curve. And then someone asks you, well, okay, great, what's the charge density? Well, you can figure that out, right? We're going to take rho v equals d dx dx plus the derivative of the y component with respect to y plus the derivative of the z component with respect to z. Let's do these separately. The derivative of the x component of d with respect to x, just take the derivative of this, which is going to be 5, back to black, which will be 5 times e to the 5x. All right? Because this right here, this e to the 5x represents d sub x. Whereas this 6x right here is d sub y. So the next step is the derivative of dy with respect to y. And since there is no y in there, it's a constant, so it just becomes 0. And then, of course, dz is already 0. So our answer is going to be that 5e to the 5x equals our charge density. So you give me any location, x, y, and z, and I can tell you what the charge density is throughout this space that we've measured things. All right. In reality, though, you're never going to have a nice, clean equation like this that you can simply solve directly and figure out the charge density. We're going to need a numerical technique that's more practical, and in the next video, we're going to introduce how you might do that, essentially by dividing up space into small pieces and approximating the derivatives by taking the differences of measurements in adjacent cells.